Okay, so good afternoon, friends, and welcome to my talk, which is last of the day. The whole day we have been hearing about twist on graphene and various layered materials, but in this talk, I'll share with you a twist on the understanding of Kondo insulators, and it's all correlated electrons. Sorry, not working. It's not working. Oh, okay, fine. This talk is based on two publications with my student Panchram, who's now a postdoc in Prague. And it was part of his thesis. And there is more work in progress. And maybe in future we will have more things to say. But what we have already done in these two papers is actually quite interesting and I would say very original. And the whole effort, of course, is motivated by these two papers some years ago, which talk about something which we are not used to, which is to say that measurements called quantum magnetic oscillation measurements reveal Fermi surfaces in Kondo insulators. Now, we are not used to thinking about Fermi surfaces in insulators. So what these experiments are actually telling us is a very important puzzle. And the calculations and the theory that we have done and developed are an effort to understand this question in the context of Kondo insulators. So even if you lose track of what I said I will say in the middle, you can at least keep this summary of our finding, which is that, so what we have found, this is our finding for Kondo insulators, and this is a reasonably generic finding. So this is, although like all calculations, everybody takes motivation from samarium hexaboride, but the results that I am presenting are more generic to Kondo insulators and not specific to samarium hexaboride. So what we discover is, through a theory that we have developed, that there is an interesting many-body reorganization of the quasi-particle spectrum that is taking place inside the Kondo insulators. And this is something which was actually not known before. And this is what I term as band inversion of charged quasi-particles. And it will become clear as we go along what these charged quasi-particles are. So what, as you can see, is that a part of the band dispersion is getting inverted. So there is some topological change happening, at least in the form, the shape of the band dispersion. And it turns out, and this is what we systematically showed, this is not just for the fun of it. In fact, it is this inversion that is happening in the nature of charged quasi-particles, which is indeed leading to the appearance of quantum oscillation. So for instance, for strong coupling, and here I mean Kondo coupling because we are talking about Kondo insulators. In the strong coupling limit, there are no oscillations, whereas when the inversion has happened, there appear oscillation. So what we are saying is that the charged quasi-particles of Kondo insulators exhibit this interesting inversion phenomena as a result of the competition between Kondo coupling or Kondo interaction and the band width. And depending upon where the system lies on this parameter axis, the Kondo insulator may show quantum oscillations or may not show quantum oscillations. So in a way, what we are saying is an underlying organizing principle that not every Kondo insulator is same, and depending upon the Kondo coupling, it may show quantum oscillation or it may not show quantum oscillation. Just for the students who may not know this effect, this is a very famous effect we all learn about in basically a short Mermin or Kittel. It's called de Haas-van Alphen effect, discovered by de Haas and van Alphen naturally. And what they find is basically that magnetization oscillates as a function of the inverse of magnetic field, and it occurs in all kinds of metals. So it's a very general effect seen in conductors of all variety, and hence has been taken as a hallmark of a metallic response. And right in the beginning, just when the experiments were being conducted, the first experiments by de Haas and van Alphen, Landau and Piles more systematically actually showed that such oscillations would indeed occur, taking free electron gas as a prototypical simple model of metals and then quantizing it using Landau quantization. So it's a consequence. The fact that there are quantum oscillations is a consequence of Landau quantization of electronic energy levels. Somewhat later, Onsager actually made this effect into an industry or a probe of serious kind. What he says that the frequencies of these oscillations actually measure some extremal areas on the Fermi surface. So actually by doing these experiments, people therefore now precisely map out the Fermi surfaces of different metals. And obviously you associate Fermi surfaces with free electrons, with metals. So you never expected them to occur, this effect to occur in insulators, but only until recently. And this is what brings us to these two, this is what makes these two papers, the first papers, very important, significant. And the story is not just limited now to samarium hexaboride. Just last year, another Kondo insulator seems to, I don't know if there are further papers supporting or not supporting this, but at least there is a report which says that another Kondo insulator also exhibits these quantum oscillations. Just as I said, the talk and the final discussion will not be dependent on samarium hexaboride as such, but just to get a hand on what samarium hexaboride shows. So this is a Curie-Weiss paramagnetic metal at room temperatures. And it actually, as you lower the temperature, it becomes a paramagnetic insulator. In fact, there is no magnetic order down to whatever few millikelvins. So it's really a quantum paramagnet down to the lowest temperatures. And the reason why we call it as a nice example of Kondo system or Kondo insulator in particular at low temperatures is because the electronic structure or the basic electronic properties of this material are governed by, so boron 6 is a sort of satisfied ligand sitting at the center of cesium chloride cell. So the active ions are samarium, and what has been long realized that the important processes here are the fluctuation between 4f electrons and the 5d electrons. The 5d being a forming broadband, they behave as conduction electron band, and 4f being very strongly localized tend to behave as local movement at the simplest level. So this is what Kondo systems are supposed to be. These are systems with local moments hybridized with some conduction electrons. This particular material was sort of, it came to the fore of discussion recently, although it has been known for 4 decades or so, or maybe more, is the suggestion by these two groups that this may possibly be an example of a topological Kondo insulators, as has been the trend of the day that you search for topological features in all kinds of systems. And so they made a proposition that this could be possibly an example of a topological Kondo insulator. Coming to the discussion of, to the finding of magnetic oscillations, the 2 experiments were conducted. The first one actually is, so let us just look at this view graph. It says that, so there are these oscillations M versus H, and then you do Fourier transform and you find some frequencies. And the order of magnitude of these frequencies, at least the authors claim, that this measures 2-dimensional Fermi surfaces as envisaged under the under this picture of topological Kondo insulator, which means that the bulk is insulating, but there are surface conducting states, and this is what is being, and it is those conducting surface states which are being revealed here in this oscillation measurement. But soon after, there was another experiment where they maybe did better analysis or went to higher fields and so on. And they could, when they did the Fourier transform, they found that they could actually resolve the frequencies up to a few thousand Teslas. By the way, these are oscillations in inverse field. So the frequency is of the unit of magnetic field. Frequency is the magnetic field. And this is 10,000 or some Tesla. And the values that they get, they claim, the experimentalists claim, actually do not correspond to anything coming from the surface. They actually correspond to the half of the bulk-Brillouin zone. So here is a situation. You have an insulator which is insulated in the bulk, and I'm right now not even bothered about whether there are surface states or not. So there is a good insulator, bulk insulator, and the quantum oscillation frequencies correspond to some areas, some surfaces which are actually in the bulk and not on the surface. So then this brings us to a very interesting question that what the samarium hexaboride is in particular, it doesn't matter whether it is topological or not, but there is something generic about the Kondo insulating bulk which is driving these quantum oscillations. So independent, so the question goes beyond whether this material specifically happens to be topological or not. Because if something is generic to the bulk, which is insulating, whether it is topological or not, then we have to find out what is that generic feature. So this is basically the motivation for this talk. It's not a survey of all that happens. In fact, here I want to point out this paper by Professor Bhaskaran. I was some years ago randomly looking at some papers, and then I found this paper by him. And that is how I got introduced to this problem, that there is a problem to be fixed. Although I do not agree with many things that he said there, but at least it motivated me to find my own answers. So let us go to the theory that we have developed. So the question, as I said, is, at least in my mind, is clear. I'm not being specific to a material. I'm not even being particular about topological insulators and so on. I'm just saying, let us look at a simple generic model of an ordinary simple Kondo insulator, which has been known for 50 years or so, and people have done a lot of theories on that. And let us just go back and see, is there something in that basic model which will help us understand whether or not there could be quantum oscillation. And this is all many-body physics. So this is not just at the level of, as I showed in the previous view graph, people have attempted to answer this question and have found answers within some simple band theoretic models of hybridization and so on. But here we are doing actually a full-blown many-body theory of a many-body model. So the simplest model that we can think of that has been known for Kondo insulators, to model Kondo insulators, is what is called Kondo lattice model. So the basic setting is you have a lattice, and on every side you have a spin half moment. For simplicity, we are just treating it as spin half. And then you have other electrons which are hopping on this lattice, which form the conduction band with hopping amplitude T. The electronic spin of the conduction electrons and that of the localized spin are interacting via what is called Kondo coupling. So this is the minimal basic model of a Kondo insulator. And when the electron filling is exactly half, so at that for that filling, this system is an insulator, and hence a Kondo insulator. The question is, the actual answer to the question that we want to find is how this model problem responds to orbital, I mean, what is the orbital response of this model problem to magnetic field? And by orbital response, we basically mean lattice version of P minus A. So Landau, of course, was doing continuum, so he could deal with P minus A square, right, kinetic energy for minimal coupling problem. And here Mr. Piles gave us this Piles coupling, that this is how you should think about coupling of lattice electron to a magnetic field. So this is the problem at hand. This already is terribly hard, and this makes it even harder. And the question is, what is the answer? Which means, if I compute M for this problem as a function of B, do I get oscillations or not? The other model that we, of course, that the first calculation was on this model, and that is where we developed all these insights and original findings. But then for consistency, we also did the same calculations for another very basic model of Kondo insulators, which is known as symmetric periodic Anderson model. In this case, we don't treat the localized electron as just spin, but as an actual electron, which hybridizes with the conduction electron. You have a hybridization term, and you have a local electron, which has strong correlation. And again, ask the same question, what M versus B results one finds. Now, it was not obvious how to proceed with this many-body problem and find answer to this terribly hard question. And in fact, many years ago, even before actually I made this public, when I was a student and Professor Krishnamurthy, Shastri, TVR were my teachers there, I invented this representation for discussing correlated electrons. The representation actually is based on this very simple map. So I think about electron as, I mean, of course, everybody knows electron has charge and electron has spin. So there are these two attributes, and can in some canonical way, I can sort of rewrite the physical electronic operators, which are C up and C down, in terms of these attributes, the charge attribute and the spin attribute. So suppose, so this is local Hilbert space. These are the physical states no electron, up electron, down electron, or doubly occupied site. And then 0 and 1 in my notation means if I am in this sector, which means there is one electron, be it up or down, I would call it having one fermion. If I'm in this sector, then I would call it having no fermion. So 0 and 1 is my this new charge degree of freedom. And plus and minus, if I have one fermion, plus and minus represent nothing but the physical spin of the electron. And if I have no fermion, then plus and minus represent the empty site or the doubly occupied site. So once you have this basic map, you can basically write all these relations. They may look obscure to some of you, but they are not. Phi is just, where is it? So phi and size are the Majorana operators, which you can always rewrite in terms of the spinless fermion that 0 and 1 represent. So basically, this representation involves spinless fermion and Pauli operators. And one interesting aspect of this representation, which in the beginning motivated me to sort of take it seriously, was that the Hubbard interaction becomes just the chemical potential of spinless fermions. And I don't know if I have it here or not, maybe not, but let me just tell you, just to give you a physical feeling of this A. A is somewhat like a Gutzwiller quasi-particle. So it carries in it the effect of local correlation. So A, although A is a canonical spinless fermion, but in terms of the physical electron, it is to be viewed as some kind of Gutzwiller-like particle, a correlated quasi-particle. And it was very useful. For example, I could, there is no time to discuss this very interesting physics of the phenomena called Nagaoka ferromagnetism, but I could actually develop a Hamiltonian description for this very difficult problem. Could make few other interesting, advances, and I think people are taking note of it now, and maybe there is something worth taking this representation seriously. So I was always interested in actually applying this representation to Kondo lattice model just as a toy exercise, but I had no motivation. But now we have a motivation that Kondo insulators do behave in this funny manner that the experimentalists reveal. And can my way of thinking about correlated electrons help us understand the behavior of Kondo insulators? So what I do is, I'll not go into the details of technical steps, but at least I'll outline the basic point. So this is my starting model, and to begin with, just to fix the basic understanding, whether in this new representation, the basic understanding of Kondo, Kondo insulators is correctly given, it comes out correctly or not, we just do it first for in the absence of magnetic field. So I just rewrite this whole thing in terms of these auxiliary variables, these charge-like and spin-like variables that I introduced. The problem actually looks terrible. I mean, not so easy, or at least this looks more elegant and simple to state. But it's not too bad. If you look at, suppose, the strong coupling limit of this problem, so J is very large, N can only be a number between 0 and 1, or if you think in terms of average, it is something between 0 and 1. Then all it says is that strong J would imply a singlet formation between sigma and tau. Tau is the local moment, and sigma is the auxiliary variable or spin-like attribute of the physical electron. So we can look at the strong coupling limit first. So in this language, strong coupling limit would basically mean forming a local Kondo singlet between sigma and tau. And if you take that as the given fact, then the residual charge dynamics is still a non-trivial. So the dynamics of these so-called Gutzwiller-like quasi-particles is still there. In fact, what Professor Bhaskaran discussed in his paper was when he claimed that maybe there is a Majorana C of some kind, he only had this in mind. So in this representation, not only you have this, but you also have a non-trivial effect of the Kondo coupling. And that actually opens up the gap. So this is, of course, what we know, that there should be a gap in the charge sector, and there is also a spin gap in the strong coupling limit. The system is Kondo singlet, and so on. So everything looks fine. And when we try to redo the same thing in the presence of magnetic field, and we will see the results maybe later, and I have to keep track of time, we did not find any oscillations. So we have a consistent theory which matches with whatever is known about Kondo insulators, but it did not give us quantum oscillations in the strong coupling limit. So I'm just to make sure that the half filling constraint is exactly satisfied, I am taking bipartite lattices and nearest node. So A and B refers to bipartite lattices. I mean A sublattice and B sublattice. But then we realize after some thinking that, well, strong coupling limit is too special, and we should actually determine the effective charge dynamics self-consistently, because in the strong coupling limit, I'm completely dropping this out, because sigma, singlet kills this term completely. Now what we do is we do a self-consistent charge in spin dynamics, where the spin part influences the charge part and the charge part influences the spin part. That is the basic spirit. We have a slightly more general problem. We can skip all the detail. And so now we again go back and see what do we find. Well, we find something what we know. As you increase the hopping, the Kondo singlet phase gives way to Nell antiferromagnetic. That is fine. So this qualitative agreement is there. The precise numerical value of TC may be different from different methods. And the system is always charge gap. So this theory gives you consistently a Kondo insulators or an antiferromagnetic insulator, depending upon you are in strong or weak coupling. But this is what we found to be something completely unexpectedly. When we looked at the detail of the charge gap, so the system is charge gapped always, that is fine. But then we asked us a simple question: where does this charge gap comes from in the Brillouin zone? And what we found that actually it doesn't always come from gamma equal to 0 point. In fact, in the strong coupling limit, the charge gap comes from gamma point, the 0 point of the Brillouin zone. For example, square lattice as an example. We did it also for simple cubic lattice. And as we increase the hopping, actually at some point the gamma point becomes a local maxima and the charge gap comes from a different non-trivial contour. And eventually, expectedly, when the hopping is stronger and stronger, it tends to the diamond, the boundary of the half Brillouin zone, as we know from the weak coupling limit. And this is when we looked at in detail about the charge dispersion, this is what we found. So, so this is what I mean by inversion. So as I increase hopping or decrease Kondo coupling, so initially two parts, so E plus and E minus in this case just means two parts of the quasi-particle dispersion. So one part remains static, but the other part is dynamic and it is changing. So the gap initially comes from gamma point. At some point Ti, the gamma becomes local maxima, and then this maxima keeps rising and eventually the entire band is inverse. So on the strong coupling side, this is the picture you should have of the quasi-particle dispersion, and all of this is gapped all the time. And in the weak coupling side, this is the picture you should have. Now, again, these are not normal electrons. These are some non-trivial correlated quasi-particles. But just for the fun of it, think about it. Imagine these are the guys which are contributing to quantum oscillation, some cyclotron orbit motion or some kind of, in some semi-classical crude picture. Then if you have two parts of dispersion like this, then one quasi-particle makes a cyclotron orbit this way depending upon the curvature, the other guy makes it exactly opposite. And that is why in the strong coupling limit, the two cancel out exactly. But once the inversion has happened, there is a possibility that the two parts of the dispersion actually add up to give you non-zero quantum oscillation. This was just a hunch, and then we actually set about to do the actual calculation. By the way, this... No, well, let us call them charged quasi-particles. Let us not call them iron. You can rewrite things in terms of, but these are not Majorana, these are actual fermions. Yeah, Majorana is a tricky term. And here I'm just trying to tell you that while this inversion is happening, there is no appearance of mid-gap states or surface state crossing. So this is not really like the topological insulator when we think about. There are no surface states appearing while the inversion transition is happening. No. No. So this is this is all ground state, zero temperature. No, the ground state doesn't have quasi-particles, but the ground state energy has contribution from these quasi-particles. Just think about, not to exactly take it serious in the same spirit, but mathematically, when we do BCS theory, the pairing term, of course, the quasi-particles in the ground state are zero, but the effect of that pairing fluctuation is also part of the ground state energy. So what I'm saying is the epsilon k's actually are contributing, these fluctuations are contributing to determining the actual ground state energy. So it's not a simple, straightforward, there's no simple way of thinking about, so it's not thermally excited quasi-particles which are leading to it. That is the point I'm making. There is no temperature here. So then what do we do is we actually rewrite the same effective charge dynamics, but now in the presence of magnetic field, and the Pile's phase factor becomes, so it's a more general version of what we know as Hofstadter problem, but now it has both hopping terms and pairing terms and so on. So the important point, maybe just in the interest of time, so remember, the net magnetization would come from both the effective charge part and the effective spin part. But first thing we want to say is that this part doesn't contribute at all. This is always much less significant, 100 times or more smaller. The second part is these wiggles, the so-called DHV oscillations on the linear or the rising part of the M versus alpha is same as magnetic field curve. This never appears for the spin part. So basically the quantum oscillation physics is being completely determined by the charge dynamics. And the interesting part is for large enough T, there is what we expected, the appearance of these wiggles or the DHV oscillation. So this is what I said earlier. If T is very small, which means if we are in the strong coupling limit, this is not oscillation. This is just the overall Hofstadter periodicity. The oscillation would mean that on this little linear rising part of the M versus B curve, you should have these wiggles. And for strong coupling limit, there are no wiggles at all. And when the coupling is sufficiently weak, there are wiggles. And in between, the inversion has happened. Okay. So let me in fact show this curve. We could actually resolve the contribution to M coming from this part of the dispersion and this part of the dispersion. And look at this carefully. In the strong coupling limit, so M plus means it comes from this part of the dispersion, and M minus means it comes from this part of the dispersion. So M plus and M minus exactly cancel each other, the very crude qualitative picture that I was trying to give you. So in the strong coupling limit, the two portions actually contribute, but they cancel out to zero. And when the inversion has happened, or just about that point, the two cancellations, the two do not cancel exactly. And when the inversion is complete and we are in sufficiently, T is sufficiently strong, in fact, they exactly add up to form a oscillating signal. So it actually, so this is not a, proof in the sense of mathematical proof, but this is a clear correlation that we have established, that only when the inversion of the quasi-particle dispersions have happened, it is only then the quantum oscillations begin to show up. Yes, please. These bands are fully empty. What I mean to say is, these are, yeah, these are quasi-particles. These are mixing, but these are, I'm saying, linear combinations of particles and holes. It's a mixed up business. It's slightly. Well, in this picture, your Mott insulator is some kind of superconductor of age. So the picture is little different from a normal, these are not normal electrons, but they give consistent, so for example, if you look at Hubbard model in my picture, the super exchange comes through pairing fluctuations of these spinless fermions that I'm talking about. So it's not an, so at least at half filling, this is not a superconductor, this is an insulator, but they, integer, precisely one. No, but this is not a band insulator. No, but that doesn't make, Mott insulators have integer filling, but they are not band insulators. I see that. But conduction electron is anyway frozen. Sorry, what is it called? The localized spin is a spin. It's not even, so I'm not even counting that. It's always there. No, one is, okay, one can say that way, but when we say half filled, it is the conduction electron which is half filled. Sorry? I think one has to sit down and do the calculation. There is no, what I'm saying is, This is not a simple free electron-like picture. No, no, no. No, but you are making case for something which is actually not there. Sorry, Subir, I may not have given you the best answer. No, what I'm saying is the dispersion, look, let us not even use the term band, for example. We have a problem at hand, which is this. We want to solve this. Okay? Now, if I expand, I mean, so the psis and phis are Majorana's, but let us use a simpler terminology, write them in terms of A and A daggers. Now, there is a hopping term and there is a pairing term. And the total energy would actually be some, the quasi-particles, the so-called quasi-particles that I'm talking about, they will be some mixed up versions of the holes of A and the particles of A. And the ground state energy or free energy in general would be a function of B, which depends on the dispersion of these quasi-particles. Yeah? Yeah, at least, no, I haven't tried different gauges because it was already hard enough to try this. But, well, I see what you are trying to say, that whether it respects its gauge invariant formulation or not. I'm not right now worried too much about those very specific details. My point is, it gives you a... Sorry? Okay, maybe we can come back to this after. Yeah, but what I'm saying is, please avoid of thinking about Ek plus and Ek minus as some ordinary electron bands. Think of Bogoliubov quasi-particles. In the ground state, there are no Bogoliubov quasi-particles, but the dispersions do influence it's like quantum fluctuations, different ways. Whenever you have pairing and anomalous and normal terms, they add up to, so even though the quasi-particles are not present, but the effect of that fluctuation is present in the free energy of the ground state. And that appears through E's, the Ek plus and Ek minus. And I'm saying the change in the nature of Ek plus and Ek minus is indeed showing up through the ground state energy, the change in the ground state energy. That is a simpler or more procedural way of telling it, apart from the jargons of the, yes? No, not in the middle. Okay, so the correct picture is this. Here is my ground state, and here is my, so as I said, just for, in order to satisfy the half, sorry, it will go beyond, just to satisfy the half filling exactly, and for some other technical reasons, I deliberately chose bipartite systems, where some of these things become, so A, B, etc. The fact that there are two parts to the dispersion just comes from that. But I could have done in principle just taking not bipartite structure, but the normal full lattice. So this is my Ek minus, and this is what I'm calling as Ek plus. This is E versus K. This is my charge gap. Okay? So this is the picture one should have in the T much, much less than J limit. And when T is much, much greater than J, the picture one should carry in mind is the following. In fact, this is amazing that this is a non-trivial theory. Apart from, there could be many details to be fixed. If we do the same problem from the weak coupling limit, J is very small. We can do some spin density wave-like calculation. Where does the gap open? Precisely at the diamond, at the boundary of, and this is what it is telling. The gap is actually tending to, the contour of the gap is actually becoming the boundary of the half-Brillouin zone. So at least qualitatively it is telling us that the picture that we know from the weak coupling limit is correct, even when you approach it from the strong coupling limit using this formulation. So the applicability of this approach seems to be wider than just the strong coupling limit or the intermediate coupling. But this is the picture you should have in mind, and this is the gap. Okay, so the two so-called two bands that I'm telling, or we are all thinking about, they are all touching each other at precisely the half-Brillouin zone boundary. So there is no gap between Ek plus and Ek minus. And the ground state is somewhere here, which has all the fluctuations of these quasi-particles built into it. That is a matter of bit of detail. And so it is through, so Ek plus Ek minus, if you actually excite a quasi-particle, will have some dispersion contribution of the, in terms of the actual particle living there. But I'm saying all this C here already has the effect of fluctuation. Think about antiferromagnet doing spin wave analysis. Right? We may not have magnetic excitation at 0 temperature, but the ground state has quantum fluctuations which come from these fluctuations which are ever present. So Ek plus and Ek minus, which are the dispersions of these quasi-particles, are actually present here. The contribution of these so-called energies, Ek plus Ek minus, is actually present in this, this vacuum or the ground state. This is a matter of sort of mathematical detail. Don't please think of them as the bands of some ordinary electron. As I said, first of all, they are not normal electrons, they are correlated electrons. I did not show you the inverse of this. By the way, this transformation which I constructed is not one way. In fact, the beauty of it is canonical and invertible. So not only that you can write electron operators in terms of A and sigma, you can rewrite A and sigma in terms of electron operators. And when, for example, you try to write A in terms of electron operators, it would look something like this. This is precisely your Gutzwiller-like operator, right? When you create the next, the down electron, there should be no up electron, or vice versa. So let me, I think my time is over, but with permission of chair, I'll try to quickly wind it up. Just a little more than 2 minutes. So anyway, I have maybe made the main point here, which is, yeah. So, so two things. There is inversion going on as a function of the Kondo coupling, and that we can establish directly that this inversion is responsible for the appearance of or the occurrence of quantum oscillation, because the contributions coming from different parts of the dispersions are actually either cancelling each other or adding up to give you non-zero contribution. And then comes, so this is in fact the actual data, M versus, so this is susceptibility M divided by field, and this is inverse of field. And you can see the oscillations become quite prominent as you go to larger and larger T. This is interesting. So if you do the Fourier transform of this data, so let us say take the tail here and just do the Fourier transform. We are not interested in the this part of the graph here, only this small field tail is more important. You do the Fourier transform, you actually find that the frequency is always peaked at, the dominant frequency is 0.5. By the way, let us also see what is 0.5 here. So I showed you that Onsager relation, that the frequency is related to the area of the of some surface. In the conventional picture, it is the surface on Fermi. It is some area on the Fermi surface. So area is directly related to frequency, and in some suitable units, f equal to 0.5 would mean half of the Brillouin zone. So this is amazing. The frequency that we are, and this was not, I mean, none of this was ever imagined that it would come out this way. So what we are getting is indeed the that not only we are getting quantum oscillations, we are getting quantum oscillations with precisely half of the Brillouin zone. Then we repeated this calculation for simple cubic lattice also, and we get the same thing. So there is a genericity about this finding, that there is this inversion that happens as a function of Kondo coupling, and only when the inversion has happened, the oscillations begin to show up, and the at least within this simplistic calculation, not simple calculation, we find that it always gives you some area on the surface of the half Brillouin zone. I think I'll just quickly, so we repeated the same exercise for symmetric periodic Anderson model, but maybe the main message is given, so I'll just skip all of this. Let me just summarize. So through an effective charge dynamics and a canonical representation of electrons, we discover inversion for the gap charge quasi-particles, and narrow and broad, because in the second calculation we actually treated the localized electrons as electrons, so narrow electrons versus broad electrons, but yeah. So the inversion is happening for both, not just the conduction electrons, but also for the narrow electrons in the Anderson case. We show that the DHV oscillations can occur in Kondo insulators as a bulk phenomena. So we are not talking about, I mean, there is no surface state here. So all of this is bulk phenomena, with frequencies actually corresponding to contours on the half-balloon zone surface. So what experimentalists are seeing that the frequencies correspond to some areas on the half-balloon zone is indeed what we are finding in our calculation. We find these quantum oscillations to occur due to the inversion of Hofstadter quantized dispersion of the gap charged quasi-particles. The conduction electron-like, this is important, although I did not discuss the details of Anderson model. The conduction electron-like quasi-particles dominate the quantum oscillations, although narrow quasi-particles also undergo quantum oscillations in some hidden way, and I have not discussed it, I will not elaborate on it. Our theory produces consistent physical picture of the inversion and quantum oscillations in both Kondo lattice and symmetric periodic Anderson models of Kondo insulators. And this point I did not at all discuss, but remember this representation in the beginning I actually had done for Hubbard model. So once I realized there is this interesting physics going on, I went back to the Hubbard model formulation in my representation, redid that same M versus B calculation. And what we find that there too in the small u limit, which means the SDW limit, the weak coupling limit of the half-filled Hubbard model, we again get quantum oscillations. So this appearance of quantum oscillations in insulator actually may be more general than just their appearance in Kondo insulators. And even in spin density wave insulators, at least one simple kind that we discussed, we do get quantum oscillation. Thank you very much.
Yeah, questions?
Sorry, I'm scared.
I just want to ask clarification on the summary.
No, please, please.
Just mention that you get quantum oscillation in ordinary insulator. I think I can understand that when the cyclotron.
In fact,
are you talking about a limit where the
in fact, yeah, so let me make a point, at least in the calculation that we did, and remember the non-zero field part was done numerically, so the system size limitation vagara will be there. But even then we did systematic calculations, and we found that the gap, the charge gap, so-called charge gap in our calculation doesn't close in the presence of magnetic field. So it is always, the gap is robust. It's not becoming a metal as a result of having applied strong magnetic field.
sentence version of the Hofstadter quantized dispersion? By that, I mean,
well, no, Hofstadter, the term Hofstadter I used here only to mean that we are talking about Piles coupling and we are doing a calculation in the same way as Hofstadter did for free electrons. So in that sense, I'm using the word Hofstadter, but my flux is not necessarily, that high flux limit.
Due to the external magnetic.
No, this is external magnetic field. No, I know, but if I see, so for example, what I mean to say is the following. So look at any of these tails. So for example, alpha is that reduced flux of the, let me define my alpha clearly. Alpha is this. So flux per unit cell in units of the flux quanta, correct? Of course, it can't be taken in this numerical calculation to be exactly very, very small in the sense of real laboratory fields. So these are still much bigger than the laboratory fields. But what we have to look at is the tendency, the pattern of the data. Pick up any one of those, let us say, look at this. Look at this. So as you see here, of course, it looks nearly flat. But then the wiggles appear and the wiggles keep appearing. What I'm saying is if, and I'm very sure, within our limited system sizes, we tried this. See, imagine like this. Just 1 second. So imagine there is a signal with 1 Hertz frequency and another signal with same 1 Hertz frequency. So the amplitude is indeed small. It doesn't look in relation to the bigger ones, it looks nearly flat. But as long as there is some frequency, it will pick up in the Fourier transform. So I'm saying in the alpha is not as small as you would like it to be in the laboratory scale, but the tendency is correct. That if I could take alpha to be very small, it would still show up this small frequency.
under normal Hofstadter spectrum, alpha is P over Q.
No. That discontinuous thing is the that is the dispersion, that butterfly and so on. M is not necessarily M is not necessarily discontinuous. I mean, it can have all kinds of things. For example, I will show you this. And this is, I mean, as I said, I'm sure there are points to be understood about this data. For example, look at this. When I resolve the contribution coming from this part and this part, they have lots of wiggles. This is, I mean, there is a strongly quantized lattice system and it will have all kinds of ups and downs. But they still add up to give you a reasonably regular data which is having frequency 0.5. So as I said, it is open to understanding in a greater detail, but the data is generated systematically and carefully. There is nothing wrong with the, I mean, one may try to understand why this is happening in a more accessible manner and so on. I don't know.
So you want to be in the large T over J, right? But you said...
No, okay. So the statement I'm making is, if you have two materials, both Kondo insulators, they are not likely to, I mean, they are not necessarily going to show quantum oscillation. It will depend upon whether their T by J is of the weaker kind or moderate kind or the stronger kind.
Okay, but
so from moderate to weaker side, it will show quantum oscillation. If the coupling is very strong, it will not show quantum oscillation.
But in the large T over J, in the bipartite lattice, the numerics say it's going to be an antiferromagnet.
Yes, it is antiferromagnet.
So that's not the Kondo insulator anymore.
No, it is not Kondo insulator, but it is some kind of magnetic insulator. And see, there are 2 points. Firstly, whatever kind of insulator it is, to show oscillations is itself a non-trivial fact, whether it is Kondo insulator or an antiferromagnetic insulator. And the second is particular to Kondo system, whether it actually forms a Kondo singlet or it forms an antiferromagnetically ordered state. So indeed, yes, you are right. Let me just go back here. So for example, Ti, the inversion transition happens somewhere here. This is Ti. So there is still this window in which system is Kondo singlet as well as showing oscillations. And of course, if T is very large, then it is not a Kondo singlet anymore. It is an antiferromagnetic insulator like SDW type. Yes?
Yeah. So can you go back to your electron decoupling?
You mean the representation?
Yeah.
The representation or the...
Yeah, the representation.
Yeah, this is the one.
In this, which parton carries an electron charge?
Well, A, or the, what is it? A operators, A and A dagger.
That?
Yeah, it's, I know what you are referring to. So if you look at this, maybe this is better, I should have written the inverse transformation also. So if I make a gauge transformation, the simple way to think about charge is that if it's a complex fermion, its gauge transformation carries the phase e to the I phi. So A under gauge transformation of physical electrons, A will become, A will both be, A and sigma both are mixed up objects. They are not very neat in the sense of, if you think in terms of the gauge transformation of physical electron, what is sure is that it carries one electron charge, but it is mix of plus and minus both. So it's not just electron, it is also hole. And sigma, for example, doesn't even carry that. So for example, sigma plus would be, let me write down. Yeah, this question is always harder to answer in some way. So there is no simple way in which, in fact, sigma is supposed to be spin attribute. It doesn't carry any charge and it doesn't carry any charge. A has some memory of the charge of the electron, but it is not just electron or hole, it is mixed up. So in that sense, it is a bit difficult. C dagger C, I'll show you what it will, just 1 second. So C up dagger C up is 1 plus sigma Z by 2. C down dagger C down is half plus A dagger A sigma Z. So Yeah, it's that's what I'm saying. So to think in terms of gauge transformation of physical electron and translate that feeling directly to A's and sigmas is it's a difficult task. So I don't want to go into that, but I want to see if the essential qualitatives of some of the things which we know from other methods are coming out right or not, and they are certainly coming out right. In fact, A happens to be like this. You can see it from here. A concerns both particle holes and also the half-filled sector. So, it's like saying you can come from empty side to this, but you can also come from doubly occupied side to this. And that is what the particle hole mixed nature of A is about. So it's like saying if you want to come to up from a doubly occupied side, you have to annihilate an electron.
Okay, last question.
Some of these things I am doing actually. Yeah. So as I said, all of this is finite zero temperature, but I am actually trying to take it further to finite temperatures and number of things to be fixed and done. Let us see what comes out.
Okay, thank you. So we'll close down the session now and you can continue the discussion.
Thank you very much. And thank you for giving me extra time.